Thank you very much. Yeah, I want to thank the organizers for having me. It's always a pleasure to come to Italy. Uh, and yeah, it's been such a nice conference so far, and so I hope that you'll find something interesting in what I want to talk about. Okay, so yeah, I want to talk about a method for computing Stokes constants of certain asymptotic series uh, using some associated quantum modular forms. So normal modular forms have very simple asymptotics as you approach roots of unity, and you just get some sort of exponential functions appearing that are convergent. And so when you have a more complicated Q series, then you get some sort of interesting sets of asymptotic series, but there's some modularity that still persists, and you can use this modularity, this quantum modularity, to really help you in computing the sort of resurgent structures associated to these. So in particular, a class of functions, say, let's say proper, Q hypergeometric functions are conjectured to be these so-called quantum modular forms, which I'll introduce exactly what I mean by that later. Please tell me if I'm writing too small, by the way, or too sort of wonky. So yeah, proper Q hypergeometric functions are conjectured to be quantum modular forms, and their asymptotics are conjectured to be resurgent. And yeah, so today, as I mentioned, I'm going to explain how from this quantum modularity, we can compute Stokes constants. And in particular, these quantum modular forms will have some sort of towers of singularities in Borel plane, and we'll get some generating series of these Stokes constants, which we can compute in terms of these original modular forms. Okay, so this is where we're headed. And so now I want to, because there's a lot of physicists here today, I want to try and motivate why we could possibly be interested in these Q hypergeometric functions and why we'd care at all about their asymptotic series. Okay, so for a little bit of motivation, so in the 80s, Jones discovered this polynomial invariant of knots. So we have some knot k. Jones discovered a Laurent polynomial invariant associated to this knot, which was some kind of the definition looked very similar to previous knot invariants like the Alexander polynomial, but there was a little twist. And so Atiyah asked, is there some interpretation of this in terms of quantum field theory? And Witten very soon after gave such an interpretation using Chern-Simons theory. So we saw from the talk this morning this Chern-Simons functional. So if M is some 3 manifold, so for example, M, you could think in terms of these knots, you could think of M as the 3 sphere minus the knot, so some manifold with boundary, but we can also consider some compact 3 manifold. And so then this Chern-Simons invariant, say on the compact manifold, we can write as some integral. So this Chern-Simons invariant takes in a connection. And so if we write this connection in terms of a connection 1 form, we have some functional of this form, which we saw this morning. Okay. And so Witten used this functional, and his idea for interpreting this invariant was that we should, instead of choosing some particular connection, we should integrate over all possible connections. And then we consider the path integral as follows. So we're integrating over, okay, let's fix our gauge group as some SU2 connections, modulo gauge. Okay, so we want to integrate this functional over this space of connections on some fixed manifold. So SU2 connections on our manifold M. And we want this to be some sort of invariant depending on this parameter n here. So n some integer. And so this would give us some interesting list of numbers, but in fact interpreting this integral mathematically is quite hard because, as we all know, defining an appropriate measure is quite tricky on these infinite dimensional spaces. But we also know that the structure of this kind of integral should satisfy some nice locality, and in fact we can use this locality to construct a set of axioms that give mathematically a theory which this should reconstruct. So this was done again soon after Witten by Reshetikhin, Churayev, constructed this mathematically using quantum groups and their representations. So this is nice because it gives us some invariance, but this original description has some clear connections to the geometry of the manifold, and in particular, this kind of integral is essentially an exponential integral on this infinite dimensional space, and so the asymptotics of exponential integrals are sort of well understood in terms of some finite dimensional, if this space was finite dimensional. So in particular, we have a lot of nice results on the resurgence of such asymptotic series and whatnot. But okay, so here these invariants that we can construct using some sort of combinatorial data associated to the manifold, they've lost this explicit link to the geometry here. And so then mathematically it becomes an interesting question as to, can we recover some of this structure that should come from this integral from these invariants themselves? And so in particular, an important point is that the critical points of this Chern-Simons functional are given by flat SL2C connections. So of course my original contour that I was integrating was SU2 connections, but this naturally lives in SL2C connections. And then the critical points of this functional correspond exactly to the flat SL2C connections. You need to be a little careful because this original functional isn't quite defined as an explicit number. It's only defined up to some ambiguity, which is why I originally chose this n as an integer. But still, we can make sense of this. And so now, the asymptotics of this integral should recover these flat connections in some way. And so in particular, it's interesting to compute this functional at a particular flat connection. And the way that you do this in general is by a triangulation. So I start with my manifold. So by the way, these flat SL2C connections, I'm sure everyone knows, are the same as the set of representations of the fundamental group into SL2C modulo up to conjugation. Okay. And so to compute this functional, this Chern-Simons functional at one of these connections, the easiest way is to triangulate the manifold. So if I want to compute the Chern-Simons functional of a connection A on a manifold M, then I write this as a sum of some Chern-Simons functionals attached to some tetrahedra, where these tetrahedra triangulate the manifold. And in particular, the geometries you attach to a tetrahedra come in a very nice moduli space. It's just one complex dimensional. And so you can in fact compute this piece of the Chern-Simons invariant on a tetrahedra. So this Z is related to the particular A that I'm choosing. This is expressed as some kind of Sorry, what do I want? Union of equals m. This is expressed in terms of some kind of dilogarithm function of these moduli. So here, this is just to give you the rough shape. And so here, this dilogarithm function is the analytic continuation of this Euler dilogarithm given here, okay? And so this is at the classical level, just computing this functional at the critical points. But to understand the full asymptotics of this path integral, people such as Hikami and others introduced some finite dimensional models for this kind of integral using a quantum dilogarithm. So instead of, so you sort of have an analogous picture here where, so say we want to understand from a manifold M, we want to understand the asymptotics of this path integral near some connection A. So we could think of deforming this contour near to one of these flat connections and trying to compute some sort of stationary phase. So we get some asymptotic series here, M, phi m of h, and I guess we need the A. Okay. And so the model that Hikami introduced was paralleling this computation with the triangulation up here. We should have this asymptotic series should come from the asymptotics of now a finite dimensional integral, where we take a product of over tetrahedra, and associated to each tetrahedra we have a quantum dilogarithm. So this this series here, we can think of it just as an asymptotic series in H. Here we're just thinking about the asymptotics. This starts as something like exponential of lead 2 of Z over H bar, and then plus a full series. So this is some kind of quantum dilogarithm. And then to construct the rest of this integral, there's a little more data because, of course, a 3-manifold isn't just the disjoint connection of tetrahedra. We want to glue the tetrahedra together. And so this is captured in this kind of integral by some quadratic form here. Okay, so this is some quadratic form related to the gluing. Of the tetrahedra. Okay, so this is just some common, this is written in terms of some combinatorics of the triangulation. Yeah, exactly, thank you. So H bar, now I want the asymptotics as n tends to infinity. And so H bar is, yeah, something like 1 on n. Thanks. Okay, so then, so this, the asymptotics of this kind of integral should be related to the asymptotics of some integrals like this. Okay, and then going back to my original interest, which was these Q-hypergeometric functions, these integrals also come as the asymptotics of certain Q-hypergeometric series. So in particular, if I replace the integrals here by a discrete sum, I replace this quantum dilogarithm by a Pochhammer symbol, and this by just some Gaussian, then I get the same sort of asymptotic series. So roughly, this asymptotic series comes from the expansion of a Q series. Okay, say I have n parameters here. Oh, I don't want to use n, m. Oh god, I don't want to use m. Okay. Okay. Yeah, of the following kind of series. So where this Pochhammer symbol we've already seen, but it can't hurt to see it again. was this finite product here. Okay, and so we're going to be interested, and we're here, Q is e to the h bar. And so we're interested as h bar goes to 1, as 0. Okay, so this is the starting point. So are there any questions on that? And otherwise, I'll get started with the proper talk. What this parameter z is? In physics, yeah, I mean, it's related to the, if I restrict this connection to the tetrahedra, then there's some finite dimensional moduli, or a one-dimensional complex moduli of geometric structures on that tetrahedra, and it describes that. So it's sort of a classical, it's describing some classical state, in a sense, on the tetrahedra. Yes? Yes, yeah, exactly. So in fact, the hyperbolic is particularly nice because the kind of description of these flat connections, there's a particularly nice flat connection on a hyperbolic knot corresponding to this geometric connection. And there's particularly nice choice of z's that can give this structure. But if you have other SL2C connections, you can construct a similar description of the invariant, and then to each of those connections, you get some value of, yes, essentially some Bloch-Wigner dilogarithm. So if you take the Bloch-Wigner, which is only half of this Chern-Simons invariant, for a non-hyperbolic, this would vanish for these cases. So the sort of the volume part of the manifold would disappear, but you'd have some interesting leftover. Pardon? No. Yeah. There's so a lot of the examples. I mean, so I'll explain a little bit. But these examples coming from false theta functions and mock modular forms generally come from non-hyperbolic manifolds. And so when you have something hyperbolic, this is when we really can't use something like mock or false. I mean, we have to go to full quantum because the asymptotic series they know about these values such as the volume and whatnot. So it's interesting, but maybe more complicated in terms of what we're going to talk about. Okay. So yeah, so yeah, I want to introduce these quantum modular forms. In the way that I like to think about them, following sort of definitions of Zagier. And then I want to talk about these asymptotic series in more detail. And their Stokes phenomenon and constants. Okay, so I want to consider, choose R, some integer, positive integer, and consider a map omega from SL2Z to GLR. So R by R invertible matrices with coefficients in some space of holomorphic functions. I'll be more precise in just a second. So consider a map such that, so one, this function on an element gamma, so let gamma, an element of here, be sort of our standard A, B, C, D. So this is a function of a variable tau, is holomorphic on the set So we take the complex numbers and we remove C inverse R, blah, 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 less than or equal to D. Maybe I want minus D, in fact. So here, this is just some cut plane in C. So maybe, so this is minus. So depending on the sign of C, we either cut in the positive or negative direction. And of course, someone should argue what happens when C is 0, because I'm inverting here. And if C equals 0, I guess we either want the whole of the complex plane or maybe the complex plane removed R. Okay. Okay, so we have some collection of holomorphic functions associated to each element of SL2Z. And I want these to satisfy a compatibility property with respect to the product here. And so in particular, I want it to be a cocycle. So if I have two elements, gamma and gamma prime, then I want it to satisfy this cocycle condition blah, 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 gamma, and then I want gamma prime tau. Okay. So what I want to call this some, I don't know, let's call this let blah, then, okay, let me just continue the definition, in fact. I won't give that a different name. Okay, so suppose we have such an omega, then I can define a quantum modular form with respect to this omega, so with respect to this cocycle, as follows. So, so a function f which maps the upper half plane, or, so I've got a bit of freedom here. So this omega extends over these cut planes to some larger region. And for this f, I'm going to consider functions from either the upper half plane, from the rationals, or from the lower half plane. But for today, because I'm interested in these Stokes constants, I'm just going to mainly focus on the upper half plane. So consider an holomorphic function, f from the upper half plane into CR, so some vector valued function. And we say that f is a quantum modular form with respect to the cocycle omega if f of gamma tau is equal to omega of gamma of tau f of tau. Okay. And in fact, I want to also be able to include some kind of automorphy factor. So if J is an automorphy factor, then I can also include it here if we want. Okay. So I was calling this omega a cocycle, and it satisfies this cocycle property here. And with this kind of description, if this f wasn't just a vector but was a matrix, I mean, it looks like this cocycle here could be some kind of co-boundary. It looks like a quotient of these two things, if this was a matrix and not a vector. But in fact, because of the domain of this function, this omega lives in some sort of smaller space than this f. And so therefore, while this looks like sort of some kind of co-boundary relation, the fact that this omega has this improved analyticity that the f doesn't have implies that it's not obviously some kind of co-boundary. So in fact, you can think of this omega as an element of some kind of non-commutative group cohomology associated to SL2Z with values in some, GLR of some kind of holomorphic functions here. But I don't know how helpful that is to you, but this group, I mean, this doesn't have a nice additive structure, and it sort of doesn't behave so well, but it's good to keep this in mind. Okay, so then I give you a definition, I should give you an example. Are there any questions on this definition? Okay. Yeah, so the sort of first examples, so obviously modular forms fall into this category. If I take this omega to be a constant with respect to tau, then this is just some vector-valued modular transformation. So then the next interesting examples, besides these sort of trivial examples coming from modular forms aren't so trivial, but would be then these mock theta functions or these false theta functions. So in particular, our first example, I'm not going to give you all the gory details, but we can look at one of Ramanujan's, okay, let me do the M. We can look at one of Ramanujan's original mock theta functions. Okay, so if we sum from k to infinity, q to the k squared plus km minus qk. Here I guess I should have given you a little more. I think we all remember the definition, but if I have some extra parameter here, I have this double Pochhammer, and I guess my shorthand from before was that this was equal to qn. Okay, so if we consider this family of Q hypergeometric functions, it looks like we have infinitely many depending on this M here, but in fact this satisfies a nice inhomogeneous second order recursion. And we've already seen these Appel-Lurk sums and these Mordell integrals before, and so in particular if we specialize this M to 0, then this has a nice identity. I'm not sure if it was originally due to Ramanujan or Watson, but we can write it as one of these sort of Appel-Lurk sums. So okay, was 1 or 2, blah, blah, blah. Okay, 1 plus qk. Great. Okay, and so we saw that these Appel-Lurk sums and these mock modular forms are somehow associated to these Mordell integrals. So some explicit integrals of some trigonometric functions with some exponentials, or some hyperbolic functions with exponentials. And so this is going to be, I mean, this is the key point that allows you to prove that this thing is some version of this quantum modular form. So what, in particular, is a quantum modular form? So I want to take a vector-valued function. The first entry is just 1, something kind of boring. And I take q to the minus 1/60th of f0, so this function here. And then I want to take one more of these functions, this f1, and multiply by q to the 11/60ths. And so I said that there's only 2 of these functions that are independent up to some inhomogeneous part, and that's reflected in this vector here. And so the statement is that this g of q is a quantum modular form. And with a specific cocycle, because of course if I have a quantum modular form I need to tell you what the cocycle is. And so this cocycle evaluated on the T matrix, so I'll use the notation T and S, I'm sure you're all familiar with, for these matrices. So evaluated on this, I have essentially a constant function here, so e of minus 1/60th, e of 11/60th, where This function e is just the e exponential to the 2 pi I x. Okay, and then the more interesting cocycle, I'll take it up, is with respect to the S matrix. And this cocycle is given explicitly in terms of these Mordell integrals. So this matrix is given, I'm not going to give you all of the gory details, I'll just give you the rough structure. But if you want, you can hassle me later. So this cocycle looks something like this. So we have some matrix here where these alpha and beta are some explicit algebraic numbers. And then in these two entries, this is equal to some combination of Mordell integrals. And so these Mordell integrals are given by some integral over r exponential of 6x squared tau plus, I guess I need an m x tau plus n x. And then one of these trigonometric functions. Okay, so where I take some combination of these m and n, and I have some coefficients in q or q tilde. Okay. But so the fact that this integral has this, the fact that this cocycle has this nice integral expression allows us to prove this analyticity property. So the fact that it has this continuation, the proof comes from this nice integral expression. Okay, but this is a particularly a simple example from the context of these quantum modular forms. And it's almost modular. You see that it's sort of some finite extension of this 2 by 2 block in the bottom would essentially be coming from a modular form, and then we're extending it by one dimension. And this is related to this fact that this Q-difference equation, or this recursion between these Fm that I mentioned, is some inhomogeneous extension of a difference equation satisfied by modular forms. And in this case, it will be related to the Rogers-Ramanujan functions. Okay, but so then we can look at these sort of class of hypergeometric functions, and I mean, we should prove that we have some large set of examples, and so this you can do. So here's a little, let's call it theorem for now, but hopefully it would be an example at some point. So if I look at some similar set of functions to this, so if I take f of q equal to a sum, and I take q to the ak squared over qk, so a is some positive integer, and I take the vector valued function, which essentially comes from a similar kind of construction as here, where I just add in some extra linear term to this quadratic form here. And so I take this vector. So the statement is that this is a quantum modular form with cocycle given with entries in the following form. So cocycle with entries. So this omega s given by, okay. So it's essentially going to be given by the kind of integrals that we started with that were related to these three manifolds. So in particular, we're going to find that this omega has entries given by an integral of now not just some kind of asymptotic expression. Now I choose a very special analytic function here called the Faddeev quantum dilogarithm. So this Faddeev quantum dilogarithm is written as some quotient of Pochhammer symbols in the upper half plane. And it has the nice property that it's holomorphic. So let's just do a little aside. So this function is holomorphic on C when we remove the non-positive reals. And so now we're going to take an integral of this function. It has the asymptotics that we saw before, but now it's some explicit function. And then against, essentially mirroring exactly this structure here. So against now a Gaussian. Where have I put the tau? Okay, I'll put it down. And again, some sort of combination here. So tau plus nz. And here I choose some specific contour, maybe something like square root tau reals. Yeah. So if you want to bother me for what this function is, this is your last opportunity. Otherwise, we can just take it as a black box. It's nice. But so the proof then is completely analogous. The fact that this co-cycle satisfies the properties that we want, that I just erased. We write this co-cycle in some integral form where it's just manifestly obvious that it extends across the cut plane that we want. So in the same way that this Mordell integral has this extension, these integrals of this quantum dilogarithm also have this similar extension property, and so we can prove quantum modularity using this. Okay. So now I've described these quantum modular forms and their co-cycles, and we want to understand how this relates back to these asymptotics of these three manifold invariants. So the asymptotics of these sums, as I already mentioned, is given by essentially a stationary phase approximation to these integrals. So in particular, I mean, we could just choose an example. So if we choose in the above formula, if we have a equal to, then this integral has the integrand has the sort of following asymptotics. It's exponential of, okay, and so we have our q equals e of h bar, and we're sending h bar to 1. Oh, it's a 0, sorry, q to 1. Okay, so then this has the integrand has the asymptotics in the following form. And so then to apply stationary phase, we just looking at the critical points of this functional here. And so if we take the derivative of this, of course, we find something particularly nice. So yeah, plus. Okay, and so then if we exponentiate this, we find a simple algebraic equation. So let's call x equal to e of z. And so we just find x to the 4 divided by 1 minus x equals 1. And so then when we apply a stationary phase approximation to this integral, the asymptotic series that come from this have coefficients in some nice algebraic number field. And these can be explicitly computed even numerically if we know the field that this lives in. Then if you have some quantum invariance and you do some asymptotics, then you can compute this number to some precision and use something like LLL to try and guess an explicit formula for this these numbers in this the coefficients of this asymptotic series. And so this is very explicit and very pretty because we've lifted. So the leading asymptotics, of course, will be given by one of these Chern-Simons invariants, but then the subleading terms will be some interesting coefficients, interesting series with some coefficients in a number field. And this number field is associated to the geometry of the manifold. So we've got some infinite list of extra information, which is quite pretty. But here, this is just some silly example. This isn't necessarily coming from a 3-manifold, but the structure is reflected. Okay, there's also other ways you can find asymptotics of 3-manifolds invariants. So there's this these kind of knot invariants you can package into an element of a ring called the Hibiro ring, and there's lots of structure floating around here, but I should hurry along so I won't describe how that goes. But so just keep in mind there are other ways that the asymptotics arise. Maybe it's not so pretty that I get a nice isolated critical point, but you can still deal with it. But okay, so the question is now, we have this asymptotic series, we can compute it exactly in an example or numerically, and then, of course, the reason we're all here is we're interested in resurgence, and so we can ask the question of what kind of resurgence does these asymptotic series satisfy? And so there's a conjecture. I'm extrapolating a little bit, so if it's not entirely true, you can't blame the original authors, but so there's a conjecture of Garofalidis, Gu Marino, which states that so the asymptotics of these Q hypergeometric functions the asymptotic series, I guess, of these Q hypergeometric functions are resurgent with Borel resummation given by how do I want to say this? Yeah, the asymptotics of Q hypergeometric functions are resurgent, and so let me get rid of this. And quantum modular forms with Borel resummation given by the cocycle omega. So, okay, what's the initial first evidence of why this could potentially be true? So if I have such an asymptotic series and I look and so if I assume that it's resurgent and I can take my Laplace transform, say along the positive reals, then if it's Borel resummable, this Laplace transform should be convergent on some half plane, and in particular must extend across the positive reals, which is all part and parcel in this definition of quantum modular forms. So these two structures are very closely related. So this is sort of maybe just the 0th order reason as to why you should believe this. And then the second reason is that you can do computations and you find that these match to hundreds of digits. As well as you can compute numerically the Borel resummation, you can find agreement with these cocycles, which you can also write in terms of some explicit integral formulas. And so, yeah, with Veronica, we're working hard for sort of some simple examples like these to try and prove this conjecture for some family of examples, and I think we're kind of close, but that I'm not going to talk about today because we're sort of still converging. But so now, we can, if we assume this conjecture, we have a lot of structure that we can use to try and understand the Stokes phenomenon. So in particular, this cocycle gives me some matrix of analytic functions which are conjectured to be the the resummation of some matrix of asymptotic series. And then it's also conjectured that they have these quantum modular forms associated to them, and they're just given by similar simple Q hypergeometric sums. So in terms of so we can use this to compute in terms of these quantum modular forms as some sort of generating series of Stokes constants. So the picture you should have in your head is we have this space of SL2C connections, and then we have some flat connections. Okay, and this space is some infinite dimensional space. I mean, we have to do some lifting to deal with this fact that Chern-Simons functional isn't quite defined. And so then we're interested in, because this original Chern-Simons integral is just given by an exponential integral, we're interested in counting some sort of flows between these things. And so to do this geometrically is quite hard in these spaces, but we can use this kind of conjecture to now we're just in finite dimensions and we can really just try and compute. And so that's somehow what we're going to do. So then the very easy proposition, essentially trivial. Okay, so if if omega is one of these cocycles, and the value for the T matrix is just the identity. Then if I have a basis, so if F is a basis of quantum modular forms, so what do I mean by that? I mean that F is a matrix, and each column of the matrix gives me one of these vector-valued quantum modular forms. And so then I have some square matrix, F. So, okay, this is what I mean by basis. And so where we have the following kind of transformation, so we know that if it's a basis, this first part just has to be given by the original definition of the quantum modular form. But then, as I mentioned, in general, we'll have some sort of automorphy factors because, as we know, for modular forms, we have different weights and whatnot. And so we'll also include that in the description here. So we have some sort of diagonal vector of weights. So if, okay, let's continue. Oh no, I already swapped these. Okay, so if we assume we have these conditions, so firstly, because the cocycle with respect to T, evaluated that T is just the identity matrix, we know that this quantum modular form has a nice Fourier expansion. And so then, if we consider, I don't know what to call it, let's call it F omega. if I consider this quotient, so if I take the co-cycle, evaluated it, what do I want? I want S, okay. S of tau, I take the inverse of this co-cycle against the co-cycle associated to S. So here, of course, this would be the identity, and I want a minus here. So then this also has a Fourier expansion, so is invariant as I send tau to tau plus 1. Okay, this is essentially trivial, so I'll leave it as an exercise. It's really just, if you write out the definition of the quantum modular form, you'll see exactly, okay, I'll give you the trick. I mean, it's really, you essentially take f of minus 1 on tau inverse, f of minus 1 on tau equals the identity, and you express this in terms of omega of minus s, or s, I guess. And here you use the formula for omega of minus s, okay. Okay, so now the corollary of this, so if we assume this conjecture, then I have a matrix of asymptotic series which I conjecture to be the resummation, I have a matrix of analytic functions which I conjecture to be the resummation along the positive reals of some asymptotic series. And then the same is true if I apply this minus the S matrix, but now, of course, in the definition of quantum modular forms, this switches which cut I have. So now I have some functions associated to a Laplace transform along the positive reals, and some matrix of functions associated to a Laplace transform along the negative reals. And these are given by exactly these two things here. And so if I express one in terms of the other, so I'd write the change of basis, which is exactly this quotient here, then this should describe for me the Stokes phenomenon in particular. So the corollary is, if this conjecture is true, then this matrix f of omega gives roughly a matrix of generating series of Stokes constants. Well, the proposition, if you assume the conjecture, yeah, so it relies on this conjecture indeed. So the logic's is kind of not so nice because, okay, if something's true, yeah, okay, but the corollary is essentially, if you assume the conjecture, then. So then, of course, the proposition becomes a conjecture, exactly. Yeah, for the same co-cycle. Yeah, exactly. And so there's a lot of freedom here. So we were talking, we've seen talks about this going to the other side and comparing a Q series in the upper half plane and in the lower half plane. And here, these functions omega naturally connect these two sides. However, the choice of quantum modular forms is ambiguous. There's, again, an easy proposition. You can check if I have two bases of quantum modular forms, then they're related by a matrix of classical modular forms. So, in a sense, everything up to modular forms is determined by this co-cycle. But from this perspective, it's ambiguous as to which basis of quantum modular forms you choose. So then if you wanted to be strict, you'd have to impose the kind of conditions on the cusps and these kind of things that we saw. Okay, so then just to finish, I want to give you a nice example where you can apply this, or where I did apply this for a closed manifold. And here, I really here I'm in either the nice case or the hard case or the not so nice case, I don't know, where we take a hyperbolic manifold. So we can apply this kind of hope or conjecture to compute these generating series of Stokes in some sort of explicit examples. Just you have to sit down and go through the computation. So I'm interested in the manifold I'll call 4112. So this 41 is related to the figure 8 knot, which it's apparently impossible to draw on a blackboard. So let's see. Okay, that wasn't too bad. And so if I take this knot and I take the complement, so I drill out the knot and then I glue in a solid torus. So I can glue this solid torus in and I twist it by 2 in one direction. And this defines a closed manifold here. And so in this nice paper of 2019, Gukov-Manolesco constructed a Q-series associated to this closed manifold. So so they constructed a Q-series using surgery on this knot and a separate series they constructed. And so I can give you the first couple of coefficients. Luckily, a lot of them are 0, so you can really okay. And so one of the things, again, this is a theorem, but hopefully at some point it's just an example. So this series, they could compute sort of term by term using some nice algorithms, and I found a very simple formula for this. Well, maybe not so simple. I mean, some Q hypergeometric formula. But if I have a Q hypergeometric formula, then I can try and look at these integrals of the Faddeev logarithm that I mentioned and try and prove that it's a quantum modular form. And in fact, you can sit down and do it. It's not so pretty, but it can be done. The end result is quite pretty, but okay, Q, and what do I have? L minus K. Does that make sense? L is bigger than K. Yep. Okay, so you can, so once you have a nice expression like this, now I can use what I know about the Faddeev and I can start writing integrals and try and prove it's a quantum modular form. And so I manage this. So this Z hat is part of a matrix valued quantum modular form. So here, I guess, matrix valued a basis of quantum modular forms. I can construct a basis of quantum modular forms. And so then if we apply this conjecture, and we can compute what should be the Stokes constants associated to this. So you have to do a little numerics, but it can be done. And then you find that, so there's then a very precise conjecture about the structure of these Stokes constants. And so an entry of this F omega Q, so this is some matrix of, it's an 8x8 matrix, so did I say 8x8? It's part of an 8x8. Okay, so an entry of this matrix of Stokes constants corresponding, so in the picture that I just erased, we saw that these Stokes constants should count some paths between different connections, and we have this Chern-Simons ambiguity, so this gives us this whole Q series. And so in particular, we can look at our favorite connection, the geometric connection in this case. And so if I look at the entry of this matrix corresponding to the geometric flat connection and the geometric flat connection. So this you can just compute. Some explicit coefficients. Okay. This agrees, and this is a conjecture, with, okay, let me give all of the names. So the gang, Nkura, extension of the 3D index of Demofta, Gayuto, Gukov. And so this is quite nice because the analogous conjecture was made for knots in the original work of Garofalidis, Gu, and Marino. And in a sense, these computations to me give very convincing evidence that not only their conjecture should be true, but also this proposal of Gang and Yonkura is the correct proposal for this 3D index, which at the moment they have a construction, but they can't prove that it's a topological invariant, which we can for the 3D index of a knot, but at least if you compute using their algorithm and then you do a completely independent computation of Stokes constants using these sort of asymptotics, then you find the same Q series up to the first 300 coefficients. So, and I mean, you could test it more, but okay, you just stop at some point because you believe it. But okay, anyway, I want to finish here. Sorry for going a few minutes over, but thank you. Good question. So there was this series of 3 papers so the first 2 were Garofalidis, Gumarino, and there they were essentially just looking for connections you could capture from Neumann-Zagier equations. But so one of the things that I found in the work I was doing on my thesis was some kind of Q series which had asymptotics that saw the trivial flat connection for the figure 8 knot. And so there you can consider you can capture these extra connections and you essentially see a similar kind of state integral to the original Anderson-Kashayev state integral, but you include some trigonometric factors like in the Mordell integral. Yeah, exactly. Yeah, so in sort of, if you give me a Q have a geometric function that's simple enough, you can kind of sit down and do the whole machinery. But yeah, and so, I mean, what would be fantastic is for these trivial flat connections if there was a way to canonically extend these state integrals of Anderson-Kashayev, which currently I can do it in a bunch of examples. Like for this closed manifold, the original integral I wrote down didn't include the trivial flat connection, but then you can do something to recover it. But this, at the moment, is at a case-by-case basis, so there's not a systematic way to sort of define an invariant that captures everything, but it indicates there should be one. Yeah. Ah, with integer coefficients. No, the fact that it's integer, I guess, would rely on this a little more structure about the original f that you have here. So so in the proof of this, you end up writing something like, yeah, you end up getting something. I think it's okay. It's this way. Uh, so you essentially get a quotient of this basis of quantum modular forms, but you wedge in the middle these signs. So you can really see here the structure of the weights, like the automorphy factors of this basis of quantum modular forms are super important here, because if I could find a base, this kind of indicates that if one of these bases has these weights that aren't all even, it's impossible to find it, because this guy's really an invariant of this cocycle. So then to get integral coefficients, you'd need some more structure on both of these. But I guess the thing with Stokes constants, you have to do some normalization at some point. So you really, if you really want the integers, then you have to be careful about what you really mean is the asymptotic series and what's the integers. But I think, yeah, in all the examples, this little bit more you can prove. Yeah. Yeah, in theory, yeah, in theory. So one of the problems with these not invariants, so you can make a statement they're all Q hypergeometric sums, okay? Because the way you construct them is using some kind of local pictures of a knot diagram, and those pieces are all sort of products of Pochhammer symbols and sums of Gaussians, and so then you just sum all these things up, but the sums in general become some huge dimensional sums, and so these integrals become very large. So if you want to do something really explicit in examples, then it becomes a little more difficult. But for 5.2, for example, like I've done similar things for the next sort of hyperbolic knot, and so this is possible, but at a certain point, I guess you want to find the general structure, because the examples start getting very hard. Yeah. Yeah, exactly. So you, different. No, I mean, so it would still be trying to compute these Stokes constants, and yeah. Ah, yeah, exactly. So here, this is these are for knots or for cusped manifolds, and then these two introduced a sort of a surgery formula for these knot invariants, which they conjecture to be an invariant, but that there's no proof of this. So there's a independent proof that these series, when they converge, so I mean you can define these series, and there's a mathematical proof that these are invariants. In complete generality, I mean, to actually compute them, maybe there's certain examples where it's easier, but this top one, yeah, is currently just a conjecture. But this, I guess, gives some evidence that these independent computations agree. Yeah. So I think to prove that such a thing would be a true invariant of the closed manifold, you'd need to, I guess, lift their construction a bit to include this kind of fusion, which at the moment they don't deal with. And then maybe if you had this, you could try and mimic the proofs of Reshetik and Churayev, because essentially a lot of these Q-series kind of invariants, the proofs that they give topological invariants are very close to this sort of original proofs. You use some explicit Q like equations, functional equations between certain Q hypergeometric functions, and these sort of, you need to check that some things are invariant under some moves on the three manifold or the description of the three manifold, and you use these identities. And so there's analogs in the Q world, Q series world. But then, yeah, then you have issues of convergence, which is always plaguing everything. Yeah. Yeah, so you compute explicitly the cocycle, but so it's not necessarily so canonical just looking at it, but when you have these Q-geometric functions, this formula, there's something somewhat natural where I can add these linear factors as I did for the example of the mock modular forms. And in this case, you find a seventh order inhomogeneous Q-holonomic module. So the rank of this matrix corresponds to the rank of the module associated to this shift. This shift is not canonical though. I mean, it doesn't, these M and N, it's not, because I mean here the number of M and N depend on how many summands or how many dimensional sum it is. So there are some sort of canonical things you can do, like these kind of defects where you maybe take out yeah, so in theory, they should be, or at least the entries of the co-cycle should be the resummation of the asymptotic series around each of the flat connections. This 8x8 matrix is indexed by flat connections, essentially. In this case, it's a particularly nice example because the flat connections are all isolated points. So you have 8 of them. And then, the structure in more general examples, I guess, hopefully we learn more and more things and but yeah, there should be some rank. So there's some work of Manolesco and anyway, I think there should be descriptions of these kind of ranks with some sort of more interesting machinery than than just the Q-holonomic module. But yeah, let me not comment on that. Thanks.